Welcome to the deep dive. Today we're pulling back the curtain on something really fundamental to modern life, but often kind of invisible: computer networks.
Yeah, they're basically the essential architecture powering, well, pretty much everything we do digitally. Sending an email, streaming a show, you name it.
Exactly. And our source material for this is a guide called The Connected World, a guide to computer networks.
And our goal today is simple, really. We want to unpack the core ideas from the guide, the components, the concepts, why networks are so important, sticking strictly to what the guide says.
Think of it as a shortcut, maybe, to getting up to speed on this foundational topic, especially if you already have some background but want the key insights from this particular source.
Right. And the guide uses a Q&A structure, which we thought was a really good way to approach it.
Yeah, it lets us tackle things systematically. We'll cover what networks are, the bits and pieces they're made of, how they communicate, and, why they matter so much now and looking ahead.
So the guide lays out about 13 key questions to structure this whole thing. Should we quickly list them out so everyone knows what ground we'll cover?
Good idea. Let's run through them first. What exactly is a computer network and why is it indispensable?
Then, what are the end devices we interact with daily?
Third, what do intermediary devices like switches and routers do? And what's the key difference?
4. How do wireless access points and modems fit into getting online wirelessly?
5, how does data physically travel? What's network media?
6. What are common network types by scale, like LAN and WAN?
7, are there other types like PANs or VPNs we should know?
8. What about the rules? What's the TCP/IP model governing the internet?
9, how are devices identified? Explaining IP addressing and DNS.
10. Can we get specific examples of networks in communication and modern business?
11, how do networks enable big advancements like AI and IoT?
12. What are the biggest challenges facing networks today?
And finally, 13, what does the future of networking look like?
Okay, quite a list. So let's dive into that first one.
Right. To start with the basics, according to the Connected World, what exactly is a computer network and why is it so indispensable in our modern world?
Well, at its heart, the guide defines it as a system of interconnected devices. Could be computers, servers, your smartphone, even smart home gadgets, IoT devices.
The key word there being interconnected, right? They're linked up for a reason.
Exactly. The whole purpose is so they can communicate, share resources, share data, access services. That interconnection is what makes it a network.
And the guide mentions the scope can vary hugely.
Oh, absolutely. It could be, super simple, just a couple of machines wired together in an office. Or it could be incredibly complex and vast, like the internet itself, connecting literally billions of devices globally.
It really drives home that it's the system that matters, not just the individual pieces and the indispensability part.
Right.
Why are they so critical?
The guide uses this great analogy. It calls networks the circulatory system of the modern digital economy and society.
That's powerful. It implies they're vital, not just convenient.
Totally. They're indispensable because, well, think about it. They enable basically all our modern communication: email, messaging, VoIP, video calls like Zoom or Teams.
Mm-hmm.
They let us share and store data, connecting us to cloud platforms like Google Drive or iCloud, or accessing software as a service.
Supports businesses, too, massively.
The entire global economy runs on them. E-commerce, online banking, supply chains, even remote work, which relies so heavily on good connections. And they're the foundation for new tech like AI and IoT, plus, access to information and entertainment.
The source even points to specific national importance, like for Canada, connecting vast distances, enabling flexible work, essential services, innovation. It's not abstract tech.
Not at all. It has very real, tangible impacts on society and how we live.
Okay, so networks are interconnected systems. The guide then breaks down the core components. It starts with the things we use directly, the end devices. What does the guide say about those?
End devices are, well, pretty much what they sound like. They're where the data originates or where it ends up. The devices people actually interact with.
Like my laptop here or my phone.
Exactly. The source lumps them into a few buckets. You've got clients. These are devices requesting services: your PC, your laptop, smartphone, tablet.
Okay.
Then you have servers. These are usually more powerful computers that provide services. They store websites, manage files, handle email delivery, that sort of thing.
Right. Providing versus requesting.
And the third category is peripherals and other connected devices. Think network printers, scanners, or those smart IoT devices, thermostats, security cameras, all that jazz.
Got it. So those are the endpoints. But the data has to get between them. That's where intermediary devices come in. The guide focuses on switches and routers as the most common. What do they do, and what's the key difference?
Yeah, this is a really fundamental distinction. The source makes sure to clarify. A switch. Think of a switch as operating within a single network, usually a local area network, a LAN.
Okay, so inside the building, metaphorically.
Pretty much. Its job is to connect multiple devices on that same network, like all the computers in an office, and smartly direct data only to the specific device it's meant for.
How does it know where to send it?
It uses something called AMSI addresses. These are unique hardware identifiers baked into every network device. The switch learns which AMSI address is connected to which of its ports, and it forwards traffic efficiently within that LAN.
Oh, okay, so it's like an internal traffic cop using unique ID cards. What about a router, then?
A router is different. Its main job is to connect different networks together. It acts as a gateway between networks.
Like connecting my home network to the internet.
Exactly that. Your home router connects your private LAN to your internet service providers, your ISP's network. Routers don't primarily use AMSI addresses for this. They use logical addresses called IP addresses. They look at the destination IP address on a data packet and figure out the best path to send it across multiple networks, maybe across the entire internet, to reach its final destination.
Okay, that's the core difference then. Switches manage traffic within one network using IC addresses. Routers manage traffic between different networks using IP addresses.
You got it. That's the key takeaway the source emphasizes.
Now, the source also mentions other devices for connectivity. What about getting online without wires? What roles do wireless access points and modems play?
Right, wireless is crucial. So the guide talks about the wireless access point, or AP. This is the device that lets your Wi-Fi-enabled stuff, laptops, phones, tablets, smart TVs, connect to the network using radio waves.
It bridges the wireless world to the wired network.
Essentially, yes. It translates between the wireless signals and the wired Ethernet infrastructure.
And the modem, what's its specific job?
The modem is presented as that critical link between your whole local network, wired and wireless, and your ISP. Its name kind of gives it away. Modulator demodulator.
Ah!
Right. It modulates the digital signals from your network into an analog format suitable for traveling over the ISP's physical lines. Could be cable, could be phone lines, DSL. And then it demodulates the incoming analog signal back into digital data your devices can understand.
So it's translating signals for the last mile connection to the ISP, basically.
That's a good way to put it. It's the bridge between your digital world and the ISP's transmission medium.
Okay, so we have end devices, intermediaries like switches, routers, APs, modems. But how does the data physically move? The guide talks about network media.
Network media is just the physical stuff, the channel that the data actually travels over. The guide breaks it down into two main types, wired and wireless.
Wired means cables, I assume?
Yep, physical cables. The source mentions common ones like Ethernet cables, those crysted pair copper ones you plug into your computer. Also coaxial cable, like for cable TV and internet.
And fiber optics.
And definitely fiber optic cable. The guide really highlights this one. It transmits data using pulses of light through thin strands of glass or plastic. The big advantages, it notes, are much higher speeds and greater bandwidth compared to copper. It's the core technology forming the high-speed backbone of the internet, especially over long distances.
Light travels faster than electricity in copper, makes sense. And wireless media.
Wireless uses electromagnetic waves traveling through the air, no physical cables needed. The source gives examples like radio waves, which are used for technologies we use constantly, Wi-Fi, Bluetooth, for short-range connections like headphones and cellular networks, 4G LTE and now 5G. Microwaves are also mentioned for certain point-to-point links.
So data travels via light pulses in glass, electrical signals in copper, or radio waves through the air. Okay. The source then moves on to categorizing networks by their size or scale. LAN and WAN are probably the most familiar.
They are, and the guide details them well. A LAN, local area network, covers a small area. Think your home, one office floor, maybe a school building.
Right. Geographically limited?
Exactly. And they're usually privately owned. The big benefit is high-speed connectivity within that local area. And a WLAN, that's just a wireless LAN using Wi-Fi.
Makes sense. And a WAN, wide area network?
WANs cover much larger geographical areas. They connect multiple LANs together across cities, provinces, countries, even globally. The internet itself is the ultimate WAN, connecting countless smaller networks. Businesses rely heavily on WANs to link up their different office locations.
So LANs are local, high-speed internally. WANs connect those LANs over big distances. Does the source mention any other network types besides these two big ones?
Yeah, it touches on a few others briefly.
Yeah.
There's the MAN, or Metropolitan Area Network. As the name suggests, it typically covers a city or a large campus bigger than a LAN but smaller than a WAN.
Okay, like a citywide network.
Right. And then there's the PAN, Personal Area Network. This is really small scale, centered around just one person and their devices. The guide uses Bluetooth as the prime example, connecting your phone to your wireless earbuds or your smartwatch, or maybe your car's audio system. It's very short range.
Yeah. Huh, PAN. Hadn't thought of Bluetooth that way. And VPNs are mentioned here, too. They seem different.
They are a bit different. A VPN, or virtual private network, isn't really defined by physical size. It's about creating a secure, encrypted connection over another network, usually a public one like the internet.
Like a secure tunnel.
Exactly, that's the analogy often used. It creates a private, secure tunnel for your data, even if the underlying network isn't secure. The source highlights how crucial VPNs are, especially now with so much remote work. They let employees securely connect back to their company's private network from home or, anywhere.
So it's about security and privacy layering on top of other networks.
Okay.
Now, for all these different devices on all these different types of networks to actually talk to each other, they need common rules. The source brings in protocols, and specifically the TCP/IP model.
Yeah, protocols are fundamental. They're just the agreed-upon set of rules and procedures that devices have to follow to communicate successfully. Without them, it'd just be noise, right? Data wouldn't make sense.
Like a shared language.
Precisely. And the TCP/IP model, the guide describes it as the practical four-layer architectural model that really governs how communication happens on the internet. It breaks down the complex job of sending data into manageable chunks or layers.
Can you walk us through those layers based on the source?
Sure. At the top, layer 4, you have the application layer. This is where the applications we actually use interface with the network. Think your web browser using HTTP or HTTPS, your email client using SMTP or POP3. It's the user-facing layer.
Okay, where the apps live, what's next?
Below that, layer 3 is the transport layer. Its main job is managing the communication sessions between the source and destination hosts, making sure data gets there reliably if needed. The source highlights two crucial protocols here, TCP and UDP.
TCP and UDP, what's the difference there?
TCP, Transmission Control Protocol, is all about reliability. It ensures data arrives in the correct order, checks for errors, and resends anything that gets lost. The guide points out this is essential for things like file transfers, email, web browsing, anywhere you need the data to be complete and accurate.
Makes sense. And UDP?
UDP, User Datagram Protocol, is the faster but less reliable sibling. It just sends the data packets out without guaranteeing delivery or order. The source explains this trade-off makes it ideal for real-time stuff like video streaming or online gaming.
Why is that?
Because in those cases, speed is often more critical than getting every single packet perfectly. If you miss a frame in a video stream, it's usually better for the stream to just continue, rather than pausing everything to wait for a retransmission. TCP's overhead for guaranteed delivery would introduce too much lag.
Ah, okay. So it's a speed versus reliability trade-off. TCP for accuracy, UDP for speed when some loss is acceptable. What's below the transport layer?
Layer 2 is the internet layer. This is where the magic of routing happens across different networks. The main protocol here is IP, the Internet Protocol. It handles logical addressing, assigning those unique IP addresses to devices, and figuring out the best path for data packets to travel through various routers and networks to reach their destination anywhere in the world.
This is where routers do their main job, using IP addresses.
Exactly. And finally, at the bottom, layer 1 is the network access layer. This layer deals with the physical transmission of data, how the bits actually get put onto the wire or encoded into radio waves. It handles the specifics of the network media being used, like Ethernet standards for cables or Wi-Fi standards for wireless.
Okay, so that TCP/IP stack application, transport, internet, network access breaks down the whole communication process logically. You mentioned IP addresses at the internet layer. How are devices actually identified uniquely, and what's the role of IP addressing in this thing called DNS?
Right, identification is key. For data to get delivered correctly, every device connected to a network needs a unique identifier. And on TCP/IP networks, that's its IP address. It's like a street address for your device in the network.
And the source mentions IPv4 and IPv6.
Yes, it points out we're in this big global transition phase. We've historically used IPv4 addresses, but there's a problem.
What's the problem?
We've basically run out. The source is clear. The massive explosion of internet-connected devices, computers, phones, servers, and especially all the billions of new IoT devices has exhausted the limited pool of available IPv4 addresses.
So IPv6 is the solution.
It is. IPv6 uses a much longer address format, providing a vastly, almost unimaginably larger number of unique addresses. The guide stresses this is essential to allow the internet to keep growing and connect all the devices coming online.
Okay, so IP addresses are the numerical identifiers computers use, but we humans usually type website names like www.google.ca. How does that get translated?
That's where DNS comes in. DNS stands for Domain Name System. The source uses a perfect analogy. It calls DNS the phone book of the internet.
The phone book. Okay, how so?
Its critical function is to translate the human-friendly domain names that we type into browsers, like www.google.ca, into the numerical IP addresses that computers actually need to locate the server hosting that website.
Because remembering long strings of numbers for every site would be impossible for us.
Exactly. DNS handles that translation automatically behind the scenes every time you browse the web or send an email. It's one of those invisible but absolutely vital pieces of internet infrastructure.
Definitely sounds crucial. So we've established networks are essential infrastructure. Can the source give us some more specific, concrete examples of the roles they play, particularly in communication and modern business?
Oh, absolutely. The source really emphasizes this. For communication, it says networks are the absolute bedrock. Think about it: email, instant messaging, VoIP phone calls, and especially video conferencing platforms like Zoom, Microsoft Teams, Google Meet. These have become completely central to how we work and connect personally, and they all run on networks.
Couldn't function without them these days. And for business.
The modern economy, the source argues, is fundamentally built on networks. E-commerce, buying and selling online, relies entirely on them. Secure online financial transactions, online banking, all network dependent.
Global operations, too.
Definitely. Global supply chains are coordinated using networks. And as we touched on before, the huge shift towards remote and hybrid work models is only possible because employees have reliable home internet access and can use secure VPNs to connect to company resources. Networks enable that distributed workforce.
It really permeates everything. The source also explicitly connects networks to enabling major technological advancements, specifically mentioning artificial intelligence and the Internet of Things. How do networks underpin those?
The guide positions networks as the essential foundation for these emerging technologies. Take the Internet of Things, IoT. You've got billions of sensors and smart devices being deployed in homes, cities, industries.
Collecting tons of data.
Exactly. And IoT is completely dependent on networks to transmit all that data back somewhere for analysis or action. Without the network connection, those devices are useless.
And what about AI? How does it rely on networks?
AI, particularly machine learning, often requires access to absolutely massive data sets for training algorithms. Networks provide the pathways to access those data sets, which are frequently stored in the cloud.
So networks feed the AI models with data.
Right. And then the source also points out, once an AI model is trained, it's often deployed as a service that people or applications access over a network. Think about using a cloud-based AI for image recognition or language translation. You're interacting with it via the network. Networks are key for both training and deployment.
It really shows how interconnected these technologies are. And beyond those specific examples, networks give us access to, well, everything else online.
Pretty much. The source wraps up this section by noting networks provide access to the World Wide Web, all of social media, countless online education platforms, and all the streaming entertainment we consume: Netflix, Spotify, Crave here in Canada, you name it. They are literally the pipeline to our digital lives.
Okay, so they're incredibly important, foundational even. But with such reliance comes challenges, right? What does the source identify as the biggest challenges networks face today?
Security is listed right at the top, and the source calls it a paramount challenge. It's a constant battle against ever-evolving cyber threats.
Like what kind of threats?
Things like ransomware, where attackers encrypt your data and demand payment; phishing scams trying to trick users into revealing credentials; distributed denial of service, or DDoS, attacks that flood servers with traffic to take them offline. The guide stresses that defending against these requires sophisticated, multi-layered strategies, and increasingly, AI is being used to help detect and respond to threats faster.
It's an ongoing arms race, essentially. What's another major challenge mentioned?
The digital divide. The source frames this not just as a technical issue, but a critical policy and social one. It's about ensuring everyone has fair, equitable access to high-speed, affordable, and reliable internet.
Regardless of where they live or their income level.
Exactly. It mentions efforts, for example, guided by the CRTC in Canada, that specifically aim to bridge this gap, for people in rural, remote, and indigenous communities who often lack the same level of access as urban areas. It's about digital equity.
That's a really important societal point. What other challenges does the guide bring up?
Network complexity and management. Networks aren't getting simpler. They're growing larger, more intricate, supporting more diverse applications. Managing these massive, complex networks manually is just becoming impossible.
So how do we cope?
The source points towards increasing reliance on automation tools. Also, technologies like network virtualization, particularly software-defined networking, or SDN, which makes networks more programmable and centrally manageable. And again, AI is playing a bigger role here too, using machine learning for predictive maintenance, optimizing performance, and ensuring reliability.
Using tech to manage the complexity of tech. Makes sense. Was there one more major challenge?
Yes, the final one discussed is net neutrality. The source describes this as a significant, ongoing public and regulatory debate.
What's the core issue in that debate?
The fundamental question is, should Internet service providers, ISPs, be required to treat all Internet traffic equally? Or should they be allowed to potentially block, slow down, or charge extra for preferential treatment of specific types of content, applications, or services?
So, could they make streaming from one service faster than another if that service paid them?
That's the kind of scenario the debate revolves around. The source presents it as a complex issue with arguments on both sides, touching on innovation, competition, and the fundamental openness of the Internet.
Okay, so security, the digital divide, complexity, and net neutrality are the big hurdles. We've covered a lot of ground, the basics, the parts, the types, the rules, the importance, the challenges. To wrap things up, the source looks ahead. What does the future of networking look like according to the guide?
The future, as the source sees it, is really defined by this ongoing quest for networks that are faster, have lower latency.
Latency being the delay.
Yeah, right, that round-trip delay. So faster speeds, lower latency, more intelligence built into the network itself, and of course, even more robust security.
What technologies are pushing us in that direction?
The guide highlights several key drivers. Next-generation cellular like 5G, which is being deployed now, and looking further ahead to 6G, these promise huge leaps in speed and responsiveness, enabling new applications. It also points to the growth of edge computing. This means moving computing power and data storage closer to the actual devices generating the data, rather than sending everything back to a centralized cloud. This reduces latency and bandwidth use.
Processing data closer to the source.
Exactly. And as we mentioned in relation to challenges in management, AI and machine learning will become increasingly integral to operating the network, optimizing traffic flow, predicting failures, automating security responses, making the whole system smarter and more self-managing.
So the source really emphasizes that networks aren't static pipes.
Not at all. They're a dynamic, evolving, increasingly intelligent architecture. The guide concludes by reiterating they are the indispensable backbone of our digital society. Their importance is only growing with trends like remote work, and they are the critical platform enabling transformative technologies like AI and IoT.
So while the challenges, security, access, complexity are definitely significant,
They are significant, yes. But the pace of technological advancement suggests that networks will just continue to connect our world in, ever more powerful, faster, and more deeply integrated ways.
it really makes you think, doesn't it? Imagine the possibilities with near instantaneous network response, or AI proactively fixing network issues before we even notice them. The evolution just keeps accelerating.
It certainly does. There's always something new on the horizon in networking.
Well, that seems like a good place to wrap up our deep dive today based on The Connected World, a guide to computer networks. We really hope this walkthrough has helped clarify some of the workings of this vital, if often unseen, infrastructure.
Thanks so much for joining us. Honestly, having a grasp of these network fundamentals is becoming more and more important for understanding the technology shaping our world.
Absolutely. And if you found this useful and want more deep dives into complex topics, breaking down key sources, please do subscribe to our channel, Tech AI and Beyond.
We'd love to have you with us for the next one.